right? I thought there'd be data. Is anyone out there?
Okay, welcome back. I'm gonna, start off by asking if you have any questions on the homework, but a couple of things I wanted to say about it first is, hope you got the announcement from Canvas that in problem 1, that coefficient 24/5 should just be 24. But also, if you did it as stated, you'll get full credit. Another thing I want to point out before questions today is on number 4, you can do this problem, although we haven't defined the gamma function. But your answer could involve the gamma function, so you don't have to simplify it. We will be doing that today anyway. And the problem 7, we're definitely covering that today. But how is it going? Are there specific ones you want to talk about? Yeah, so let's look at 5. Share my screen. So this is trying to prove my claim that you don't need to find the marginals, that if your joint PDF factors into a pure X part and a pure Y part, that's enough. And so what you have in number 5 is you have a joint PDF, and we've got an X part, which includes the indicator. So G is some set. Problem 5 says, if you can write the joint PDF this way, whereas the indicators suggest this indicator only depends on X and this one only depends on Y, then that's enough to say they're independent. So to prove this, I would take this and find, so prove independence. So one, I would just, actually this is the whole step, find the actual marginals and show that they factor and that comes because of this. So find the marginal for X by integrating over Y, and the marginal for Y by integrating over X, and then show that those multiplied together will give you the original PDF. So then show, and that's how we can prove that it's independent, because then we will have shown that it's going to factor into its marginals. The only slightly tricky thing here is matching up the constants. But any constant you get, I would keep in mind that the original joint PDF as a double integral has to integrate to 1. That might help you say that certain constants have to be equal to certain other constants. Other questions? Yeah, to prove something is not independent, then you could use our new result about the X part and the Y part, but formally the way anyone approaches proving not independence is either they compute the marginals and show that the joint PDF cannot be factored that way, or they compute some example like an expected value of X times Y and show that it's not the expected value of X times the expected value of Y, which has to happen when they're independent. So you just have to exhibit something that fails that should hold for independent random variables. Other questions? Yes.
Because
So
it was awfully hard to make it fit.
The quick thing I can do here is tell you the formula we're going to derive today. So if you have X with a PDF F sub X, or in this case, it's just called F, and Y is some function of X that needs to be invertible. So I know the square does not look invertible here, but if you look at the PDF given in 7, X only lives on 0 to infinity. So you can invert Y equals X squared on that region. So today we're gonna show that the PDF for Y is the PDF for X with the inverse function plugged in times the derivative with respect to Y of the inverse function of the inverse G. So we're gonna derive that today, and that's the formula you should use on 7. And then in terms of matching things, suppose you do a transformation like this, and I'm gonna start calling this our G inverse formula. And you get and this is not 7, but you get something like, I don't know, you get some nasty constant divided by some other weird constant plus the nasty constant. This is just, nasty constants. And then you get like y squared and 1 minus y cubed. And whether or not you drag the indicators through or worked it out on the side, you get this indicator. So I do want to say something about matching the distribution, because you may do 7 right and still have a hard time matching the distribution. So this is a continuous random variable, as evidenced by my interval notation. I'm not using brackets, that just includes 0 and 1. So you go to the continuous time of the table, and the first thing I would do is look at the indicator, because there's only 2 distributions on the continuous side that have finite supports for the PDF. One is the uniform distribution, which is an equally likely kind of flat line distribution. And that can take any values from, I don't have the table in front of me, but I think I have it as alpha to alpha plus beta. So that could be 0 to 1. And the other one is so-called beta distribution. So again, the first thing I would do to match it is go to the right side, discrete or continuous. The second thing would be to look at the indicator and narrow it down. And then between those 2 distributions, this guy is clearly not uniform. We haven't talked about that yet, but hopefully you know that one. It's just a flat line distribution, equally likely anywhere. So if you're going from the interval from 0 to 1, the height is 1, so that the total area under that rectangle is 1. But if you're going from 0 to 2, the height has to be 1/2. And this is more complicated than that, because I've got a y squared 1 minus y cubed. So the only other distribution that appears to match on the table is the beta distribution. And so in the table, you're going to see this PDF, f of x equals this stuff, b minus 1. And a and b are just parameters, and they have to be greater than 0, but they're just parameters for the model. And this looks a lot like that distribution. Of course, I have y's instead of x, but it appears that I have y squared being y to the 3 minus 1, and then 1 minus y cubed. It appears that the b is 4. And then this is something called a beta function, which we're going to define this week. But you don't need to know it, because if you did the transformation right, you are guaranteed to get a PDF. That is, I'm going to scroll back. We can integrate this and integrate this and have like a dy kind of thing over here. And we can show that this is a valid PDF in that it is non-negative and still integrates to 1. So as I was saying with the exponential, which seemed a lot simpler, this constant, or whatever you got, has to be the right constant. So if you can match up the part with the variables, including the support, these must be the same. You have no choice. It's like saying I got a PDF, an ugly blah times e to the minus 3x on 0 to infinity. Well, we know a PDF on 0 to infinity that looks like that is 3 e to the minus 3x. Like your blah can't be something different, or it wouldn't integrate to 1. And 7, you should use this formula that we're going to derive today. And then don't be so concerned about the constants you see. Just try to kind of match up the variable parts with the x's or y's. So we are in chapter 1, which is sort of pre-math stat, but not prerequisite anymore. So I call chapter 1 4 important tools you need for mathematical statistics. And I believe section 1 is just like a little intro. So maybe this is section 1.2. I'm going to write, I don't know, 1.1 or 1.2. I want to talk about univariate transformations. And then along the way, I wanted to introduce you, which I know some of you have seen this, but introduce you to a couple of other distributions. So here is a new, in quotes, because most of you have seen it, but a new distribution. So last week, we defined a geometric distribution. We had a sequence of trials of an experiment where each trial could be success or failure. They were independent. and we had a common probability of success on every trial. We called it P. And I'm going right now for the binomial distribution. And that means we have a fixed number of trials. And we've got success or failure on any one trial, probability P of success on any one trial. The trial outcomes are independent. And we want to count the total number of successes in a fixed number N of trials. So I'll just write this really briefly. We have trials of an experiment, and we have success or failure on any one trial. And let me squeeze into the top of this definition, independent trials. So I don't have to write another bullet for that. We have little p is the probability of success on any one trial. And we're going to let x be the number. I need to add more to, I could get away with putting it down here, but I want to add to the first part. We have n independent trials of an experiment. Okay, so I'm going to let x be the number of successes in the n trials. So we say that x has a binomial distribution, and there's two parameters here. We need to know n and we need to know p. So x has a binomial distribution with parameters n and p. And we write, and almost everyone writes this, x squiggly line bin n and p. Or you can write out the word. Some people use just a b, which can be confused with Bernoulli. And sorry that went so fast, but I think you've seen it. So I didn't want to bore everyone, but I did want to at least introduce it in case you haven't. Okay, so we are in this section called univariate transformations. And so I'm going to call this like part A of, no, you know what? I'm going to start a big running list. So 1 in a circle in a box, so we can recognize it because this list is going to go on for a few classes, is the first of the 4 important tools. So this is the univariate transformations. So the 4 important tools, they're going to be numbered in a box. Okay, so part A of that is discrete transformations. Oops, well, I forgot to derive the PDF. Looks like most of you were nodding that you've seen it. Here's a super quick derivation. So we've got n trials, 1 trial, 2 trials, 3 trials, up to n trials. And we're throwing down a bunch of successes and failures. And x is the number of successes in n trials. So the probability that x equals x is going to be the probability that we see S, F, S out through S, where there are exactly, this is horrible. I'm squishing this in a corner because that's not the end of the probability, but there are exactly little x s's plus the probability of F, F, S, F, where there are exactly, why I tried to squish this in. We have to list out all possible ways where we have n things and exactly x of them are s. And so these are disjoint events, and there's more. There's many more here. I just didn't leave myself a lot of space for it. These are disjoint events, so to find the probability that one of them happens or another one happens or another one, it's like a union, and we get to add the individual probabilities. But all of those probabilities of those events I just circled are exactly the same. They're all going to have p raised up to the number of s's, which is given by x here, and then they're going to have 1 minus p to the rest of the, we have n trials, so n minus x. And then we have to put a coefficient here that counts them all up. So that was in chapter 0 review, but the coefficient would be the number of ways to choose exactly x positions out of those n positions, which is read n choose x. And this lives on the discrete set 0, 1, up to n of x. So that's the PDF for the binomial. We're in discrete transformations, and in the case of discrete transformations, my advice to you is not to use a formula, but just do the transformation. So here is an example of a discrete transformation change. So I'm going to say, suppose that x has the binomial distribution with parameters n and p, and I'm going to let, it's going to be a pretty silly transformation. I think you know what the answer is already, but I want to find, I'm going to let y be n minus x. I want to find the distribution of y and name it. But you probably already can figure this out, especially if this was not your first time seeing the binomial distribution. If x is the number of successes, then n minus x is the number of failures. So it's just going to be another binomial distribution where we've interchanged the role of success and failure. Let's just quickly do it though. My advice for any discrete transformation is just do it. I don't mean to look so, Nike or whatever. I can't make that swoosh, but just do it. I don't want to give you a formula for this. Just do it. So just do it means, so let's find the PDF or PMF, if that's what you're calling it in the discrete case, for y. So that is the probability that y equals y because it's nice and discrete. And all I know about y is that it's n minus x. So let's plug that in. And I do up here know things about the probability that capital X is equal to any number I want. So I'm going to solve for x. This is the probability x equals n minus y. And then I'm going to plug this n minus y in for x in my PDF for x. Like, you have no other choice. So the PDF for y, write down what it is, then plug in what y is, then solve for x, and then use the fact that you know probabilities for x. Okay, so using the thing up here, that the PDF for x, it's going to disappear right now. This is n choose x, but in for x, I'm going to put n minus y. It is p to the x, but in for x, n minus y. It is 1 minus p to the n minus x, but in for x, n minus y. And I'm even going to do the indicator all at once. So I had an indicator on the set 0, 1 through n. And in for x, I'm going to plug n minus y. So it says to name it because of that combinatorics thing there, and the fact that there's only a couple on our table that have that. You may already be able to do this, but let's simplify it and bring it on home. So, 5 choose 3, for example, is 5 factorial over 3 factorial, 5 minus 3 factorial. And from that, you can see that it's going to be the same as 5 choose 2, because that's just a symmetric kind of definition. So to get the PDF into what looks like more like the form on the table, I can rewrite that combination n choose n minus y as n choose y. Or for the same reason that this little example of 5 choose 3 is also 5 choose 2. You just need the numbers in the bottom to add up to the top number. I got the 1 minus p once you cancel all this stuff out. I have that to the y. I'm going to write that first, not that you have to, and then I'm going to write my p to the n minus y. And then I'm going to finish up with an indicator. And for that, okay, so you can leave this on, but I think that's kind of bad form because you're trying to give a function of y. And so you should tell the reader what values y can take on, not what values n minus y can take on. So if you just look at this and kind of consider all the possible values that n minus y can take on, and then you solve for the y's, you're just going to get that y's can take on the values 0 through n. Doesn't matter what order they came in. I get an indicator here that says that y is between 0 and n. So that was my point of doing this simple example, just to talk about changing indicators, changing combinations, but my advice for you is in the discrete case, don't try to use a formula, just start writing it out. And what we see here is the PDF for the binomial distribution, but the P has been replaced with 1 minus P. I mean, they've changed positions. And yeah, and that's all that's really changed. So Y has the binomial distribution with parameters n and 1 minus P. And we kind of saw that coming because X is the number of successes in n trials and Y being n minus X is the number of failures. So failure probability is 1 minus P, call that success. I will slow down for the next part, but any questions? Yeah, that formula I gave you to do problem 7 is only for continuous distributions. Yeah, sorry. Well, we're about to derive that now, so we'll see why. And let's do it. Let's go to part B of 1 in a circle in a box. And this is going to be univariate transformations of continuous distributions. Or, yeah, continuous random variable transformations in 1D. So suppose we have X with, and I guess I want to emphasize this, so I'll write continuous with PDF f sub x. And suppose we have Y that is a function of X. And suppose that it is invertible and differentiable. It doesn't have to be, but it does for this formula. The formula that I showed you at the beginning has a derivative of an inverse in it. That's not to say you can't do transformations, but we're deriving a formula in this case, so differentiable. So let's find the PDF for Y. So it sounds like Sage did the right thing when he already did his homework with CDFs. I'm going to start with CDFs. In the A part for the discrete random variables, and don't write this down because it's wrong and I'm about to erase it. I just started off with like the probability that Y equals Y, and then I plugged in the G of X, and then I tried to continue. But this is always 0 for a continuous random variable, so I can't do this. That's not what the PDF is anymore. So that's not going to work. But I can talk about, cumulative probabilities. I can talk about a continuous random variable being less than or equal to a number. So that's what I'm going to do. I'm going to use the CDF, and I'm going to break up this proof into 2 cases. So case 1, I'm going to assume that G is increasing. If it's invertible, it has to be strictly increasing or strictly decreasing. So this is the increasing case. And note that this implies that G inverse is increasing. I guess in 5520, I would show that. Should we show it? Okay, here's how you show it. So I won't take you through the steps, but I'll, so to prove this, right, I'm going to take an x1 less than x2, and I want to show that G inverse of x1 is less than G inverse of x2. That would mean it's increasing. And so I would start off by supposing it's not. So suppose G inverse x1 is greater than or equal to G inverse of x2. I'm going to take G of both sides. Because G is increasing, it is going to keep that order, right? If I have a number bigger than another number and a function G that's increasing, then G of that big number is still bigger than G of the small number. So take G of both sides here, and I guess I might as well finish. It's only one more line. Because G is increasing, it will maintain that order. And then you get cancellation, and you'll get x1 greater than or equal to x2, which is a contradiction from starting with x1 less than x2. Oops. Contradiction. Another real quick way to think about it is maybe you remember that inverse functions are mirror images over the line y equals x. So if you have like some kind of increasing function and you mirrored it, it's going to change the concavity maybe, but it's not going to make it suddenly decrease. Okay. Okay, so case one, I'm assuming that g is increasing. I'm allowed to do this because it's invertible. If it turned around or got flat, you wouldn't be able to invert it unless you brought in a generalized inverse. So it's increasing. We just showed that means that the inverse is increasing, and we are ready to go. So I'm going to consider the CDF for y, which is defined to be the probability that y is less than or equal to y. And then I'm going to do what I did before. In the discrete case, I'm going to plug in what I know about y. It is g of capital X. And then I'm going to apply g inverse to both sides of this. Just like the same idea in the discrete case, I'm trying to solve down for the x on one side. And here I'm using the fact that g inverse is increasing so that if I apply it to both sides, it's not going to change the order there. Okay, so on the left side, I get cancellation down to x, and on the right side, I get g inverse of y. And this is, so I didn't remind you, but I started with a CDF for y. And this is the CDF for x that I'm going to call capital F sub x, evaluated at g inverse of y. Is everybody okay? Scrolling through to see if anyone's exploding. Okay, so we want to find the PDF though. So we have that, and we're still in this case where g is increasing. We've related the two CDFs, the cumulative distribution functions. You get a CDF from a PDF by integrating, and you get a PDF back from a CDF in the continuous case by taking a derivative. So this is going to imply that the PDF for y, which is the derivative with respect to y of the CDF, is the derivative with respect to y of the CDF for x with g inverse y plugged in, which is the PDF for x, and then by the chain rule, I have to multiply by the derivative with respect to y of g inverse of y. And because g is increasing, and that implies that g inverse is increasing, this derivative is greater than 0. So you weren't supposed to know what was coming, but that formula with the absolute value, you can put an absolute value there. It's the same thing. And this thing makes sense. You know, the original PDF had to be greater than 0, and this had to be greater than 0. And the only thing you really need to have a PDF is that it's greater than or equal, that it's greater than or equal to 0 and integrates to 1. And if you did the integral of, get a color, if you did the integral of this guy and then did the integral of this guy with respect to y, through a change of variables, you can get the 1 out of, you know, this is like your dx, and maybe I'll do it next time. I just want to get through these transformations. Okay, so that was one case. And the other case, case 2, g is decreasing. If I wrote that out or used it, no, case 2. G is decreasing. And this parenthetically implies that G inverse is decreasing. Same sort of argument we had before, or you can use what we did before. You could say, suppose G inverse was increasing. Well, the inverse of that is G, which then must be increasing, but we said it was decreasing. So there's a contradiction. But this implies that G inverse is decreasing. And for those of you that was not immediately apparent to, that's fine. And I know I've been saying things really fast, but I'm just trying to convince you that if you had to sit down and write it out and figure it out, that you could, more than convince you of the increasing and decreasing. Okay, so I'm going to find the CDF for y again. This is the probability that y is less than or equal to little y. This is big Y is G of big X. Solving for X, I'm going to apply G inverse to both sides, but if you apply a decreasing function, let me quickly draw something over here. If you have a decreasing function and you have one sort of number smaller than another number, then when you evaluate the number at that function, you get something bigger, which is going to make this inequality flip. So that flips since G inverse is decreasing. On the left side, I can cancel those G and G inverses. Now I want to relate this back to the CDF for X. I'm going to flip this around. This is 1 minus the probability that X is less than G inverse of Y, the complement of that probability, which is not quite the CDF if X was discrete, but since X is continuous, this is the same thing as having less than or equal to there. Since X is continuous, we're just integrating area under a curve, and whether we include the line we're integrating up to doesn't change that probability. And so what we have here is the CDF for Y written as 1 minus the CDF for X evaluated at G inverse of Y. And then we can get the PDF by taking the derivative, another chain rule action. And then take the derivative through, and you get the derivative of the CDF is the PDF, but there's a 1 in front, a 1 minus, so we get negative the PDF for X with G inverse Y plugged in. And then we get, by the chain rule, the derivative with respect to Y of G inverse Y. And at first, that negative up front is looking bad, right? You can't have a negative PDF, but because we're in the case where G and hence G inverse is decreasing, this is strictly negative. So between these two things, like the whole thing is not negative. And in fact, I could just move this negative over here, then it would become positive. Equivalently, I could take the absolute value. So yeah, I don't know if I should write that as a line, but the case is to, let me write one more line here. So this is fx G inverse Y times the negative of d dy G inverse Y, which is now positive. And so we can combine the two cases by putting an absolute value there. So I'm just going to write combine both cases. As the PDF for Y is the PDF for X with G inverse Y plugged in times the absolute value of the derivative. If g was increasing, then that derivative is positive and the absolute value is meaningless. If g was decreasing, that derivative is negative and the absolute value is going to turn it positive. So there is a formula in a box. That's not a box. I don't know what that is. I am really anti-formulas in a box. The whole reason I went into math is because my memory sucks, and you can just kind of come up with it yourself, whereas you can't come up with answers on a history exam when you don't know who did what in what year. But this one, I'm not saying you should memorize it. I'm just saying you will, because you'll use it a lot, and eventually it's just a formula you're going to pull out of your memory. Okay, I know that was really fast. Is there anything I can clear up? Okay. Oh, I screwed up again with the video. So after class on Friday, I immediately uploaded it, but I got an email last night saying it's not there, and that's because I didn't set the permissions so that it was viewable. So I'm making a different mistake every day, but hopefully I'll get this up pretty fast today. I'm going to immediately upload it, unfiltered and uncut, and then edit it and upload that later. And one of the things I edit out is if you guys appear in it, if you say something, or sometimes if your mic is on and you just make a noise, hit your pencil on a table, it'll focus on you. So it's going to be unlisted until it's an unlisted video until it's edited. So I'm not like putting any of you guys out there on YouTube. Okay, so it's hard to know who I'm talking to. I'm going to try to set up some meetings this week and next week to talk to you guys one-on-one just to see you and know who you are. But I'm not sure who asked the question at the beginning. If you use this on problem 7, you should be able to name the distribution. You may not recognize the constant, but it doesn't matter given the conversation we had earlier. And so whoever asked that, is if they still have a question at this point, let me know. Okay.
That was me.
Okay.
I have my camera off, but
Okay.
yeah, no, I'll come follow up at office hours.
Okay.
Just to clarify something, but that's very helpful. Thank you.
Yeah. So as my one example of this continuous to continuous, I want to introduce a new distribution that some of you may have seen. So we're kind of still in one in a circle in a box, part B, univariate transformations for continuous random variables when the transformation is nice and the inverse and the derivative exists. By the way, if you had to do something like problem 7, like number 7 on the homework, so you've got a PDF for X, which has some stuff in it, and it lives on 0 to infinity for X, and then you have Y equals X squared, which is like your function of X. So I was saying earlier, this is not an invertible function in general, but it is invertible where it counts for X in the interval from 0 to infinity. So you can go ahead and use this, but you could do this transformation. So this is another problem that I'm not even gonna really bother to write down a PDF for. So suppose you had another PDF, oops, and this one had an indicator that said, it wouldn't even have this, but this has an indicator that says X is anywhere from minus infinity to infinity. You wouldn't write that down because that's 1 everywhere. So why don't you just go around this week and multiply everything by 1 in all of your classes just to be, I don't know, it wouldn't annoy me, so I don't know what I mean. To be annoying. So suppose you have another X that lives on minus infinity to infinity. Then this function that I wrote above is no longer invertible on that interval, it's a parabola. So all that means is you can't use the formula in the box, but you can still do what we did. So this guy is not invertible now. And that just means you can't use our new formula. But you could approach it the same way, and I won't finish it. I can't. I didn't even write down a PDF. We could approach it. I was thinking 250 again. I wouldn't have said this stuff if I knew we were ending in 3 minutes. We could approach it the same way. So I would say I would go for the CDF of y, and this is the probability that x squared is less than or equal to y, and then try to figure out what region this is in terms of x. And in this case, it means that x is between the negative square root of y and the square root of y. And keep going, like just do it. One more. Oh no, my screen is frozen. I can write, but I can't scroll. Oh, okay. The next line of this, you want the probability that you're between these two things. So it's the probability that you are less than or equal to the square root of y. So that's like from the square root of y. Again, I'm not sure if I'm mirrored. I can't even do it if I'm not mirrored right now. From the square root of y all the way down to minus infinity. And then you want to take away the stuff that is below the negative square root of y. This is a strict thing, but the strictness doesn't matter for the continuous case. This is the probability x is less than or equal to the square root of y minus the probability x is less than or equal to the negative square root of y. And this is the CDF for x minus the CDF for x, and etc. The point being that you can do it the same way we proved this. It just doesn't fit into the proof because it's not increasing or decreasing or invertible. I think, getting all my clocks. I don't think I have time to really say much more. So we're going to start off next time. I'm going to define the gamma distribution. I'm going to define and tell you properties of the gamma function that you see in the gamma distribution. And we're going to do an important transformation of the gamma distribution using our new formula that we're going to use almost every day in math stat from the middle of the semester on. And then we're on to bivariate distributions, section 2, and that's going to be really fast because I'm just going to write, it's a generalization. Look, believe this. We're not going to prove it so that we can move on to section 3. So we're going to get through 2 and 3 next time. Or 3 and 4, if my 1.1 is an intro section, I don't remember. But important properties 2 and 3, important tools 2 and 3. Okay, I'm out of time. Thank you.